Yo, what's going on guys? Tanmay for Simple Snippets and welcome back to another video tutorial under network security, and today we are going to be taking a detailed look at an asymmetric cryptography algorithm which is known as RSA algorithm. So if you've been following this entire playlist of network security, information security, we've been covering a lot of big algorithms, especially the symmetric ones like DES, IDEA. We've seen Diffie-Hellman key exchange, and if you have missed any of the previous videos, you can check out those videos in this playlist. Today we are going to be taking a look at an asymmetric key algorithm, and we already know what the difference between symmetric and asymmetric is. So RSA algorithm, which was developed by Ron Rivest, Adi Shamir and Len Edelman. So that's why the name RSA, that is their initials R, S and A. And it is one of the most popular and proven asymmetric key cryptography algorithm. So the main crux of RSA algorithm is on the mathematical fact that it is easy to find and multiply large prime numbers together, but it is extremely difficult to factor their products. So this is the crux of RSA algorithm. So if you are making a note or if you are preparing your answers, you can note this point. It is very important. So what it says that you can select large prime numbers and multiply them easily, but it is very difficult to find the factors of that product, of that result. So this is the basic mathematical crux. And this is just an overview of asymmetric key cryptography if you probably have forgotten or if you don't know how it works. Basically what happens is, in asymmetric key cryptography, every user has its own public key and private key. So one key is public, which is available to everyone on the network, and one is private. So you can see in the diagram, Alice has her own two keys, public key and private key, and Bob has his own two keys, public key and private key. Now the encryption goes as follows. So Alice takes the plaintext PT and encrypts it using her public key. So she takes this public key and performs encryption. She gets the ciphertext and sends it on the internet to Bob. Now when this ciphertext is received at the Bob's end, what he does is he takes his private key KD and then decrypts it to get the plaintext. So you can see there are two different keys involved. One is public key of Alice for encryption and private key of Bob for decryption. Similarly, the other way around, if Bob had to send a message to Alice, he would take the plaintext, he would take his own public key KE, apply it to the plaintext, get the ciphertext and send it over the internet to Alice. Alice would read this ciphertext and use her private key KD. So Alice would use KD, which is her own private key over here, on the ciphertext to get the plaintext back. So this is how communication happens in asymmetric key cryptography. Okay, so now let's move on to the actual algorithm of RSA and how it goes step by step. And then later we'll also see an example. So that's when the idea will be very clear to you. So this is the algorithm steps. You can see 1 to 4, and then we have encryption and decryption. I'm just going to read it line by line, and what we'll do is we'll see an example, because only then you'll understand how the algorithm is basically working. Because just by reading this algorithm, you won't really understand the working of the RSA algorithm, that is in the practical sense. So step number 1 is to choose two large prime numbers P and Q, okay, and then we have to calculate N, which is P star Q, that is P into Q. So then we get a huge number. Now to select the public key, so we know that in asymmetric we need two keys, right, for encryption and decryption. So this is, we are talking about the public key, that is for encryption, and we are considering it E, and it has to be such that it is not a factor of P minus 1 and Q minus 1. Okay. So what we will do is side by side we'll take the example also so that you understand it very well. So according to step number 1, we are taking two large prime numbers P as 7 and Q as 17. Now these numbers are obviously not really large, because for simplicity purpose we are going to perform all the calculations of the algorithm as well, right? So that's why we are taking small prime numbers, but in reality these numbers are very large, and that's what makes the entire algorithm very complex to crack, and that is the basic crux of this algorithm, right? So that's why in reality the prime numbers are very large, with an order of 9 or 10 digits or even more. So yeah, step number 2 says calculate N is equal to P star Q. So let's see what N is in our case. So in our case, N is equal to 7 into 17, that is P into Q, which is 119. Moving on to step number 3. Now we have to select the public key, that is the encryption key E, such that it is not a factor of P minus 1 and Q minus 1. So in our case, P minus 1 is 7 minus 1, which is 6, and Q minus 1 is 17 minus 1, which is 16. So let's see that. So this is step number 3, that is p minus 1 star q minus 1. So it has to be multiplication over here. Okay, so let me just make that correction over here. So this and represents multiplication. Okay, so in the step number 3 we are multiplying p minus 1 and q minus 1, and for us p is 7, q is 17, which is 6 into 16, which is 96. So we have to choose a number e such that it is not a factor of 96. So I hope you know what are factors of any number. That is basic mathematics. So let us choose the public key value e as 5, because 5 is not a factor of 96, right? So we are selecting e equals to 5, which is our encryption public key. Now let's move on to step number 4. Step number 4 says that select the private key, that is the decryption key d, such that the following equation is true. And the equation is d star e, the whole mod of this entire number, that is p minus 1 star q minus 1, is equal to 1. So we have to select d such that when d is substituted in this entire equation, we get the result as 1. Okay, so let's see that in step number 4 in the example. Okay, so this is that equation, d star e mod p minus 1 star q minus 1 equals to 1. So what I am choosing is, let us choose d as 77. Okay, now I already know all these values, but you can select your own value and put it in this equation and get the result as 1. But for simplicity purpose, I've already calculated this values. So I'm choosing d as 77 because 77 star 5 mod 96, and this mod 96 is coming from this equation, that is p minus 1, that is 7 minus 1 star 17 minus 1, and when we multiply this we get 96, right? You can see it over here also. So that's why 77, that is the d value that we are assuming, we have put over here. E we've already calculated as 5, and mod 96 is this part, okay, which is equal to 385 mod 96, which gives us 1. So I hope you know how to calculate mod. If you don't, you can use a scientific calci to calculate mod, and basically mod operations are used to limit the value in certain range, and it takes the remainder instead of the quotient when we perform the basic division. So just to give you an example, let's say we are dividing 34 by 11. We know 11 threes are 33, and then 1 is going to be the remainder, right? So when we say 34 mod 11, the answer is going to be this remainder, okay, that is 1. Okay, so this was modulo operation. Anyways, moving ahead, now we have selected d as 77. So I'm just gonna say d equals to 77, which is going to be used as decryption key. So we have our encryption and decryption key by step number 4 from the algorithm. Now the encryption goes as follows. Calculate ciphertext CT from the plaintext PT as follows. So CT is going to be plaintext raised to E mod n. So this formula is going to give us ciphertext, and when we are decrypting it back, we are saying plaintext is equal to ciphertext raised to the decryption key mod n. So you can see while encrypting we are using E, which is the encryption key, and while decrypting we are using D, which is the decryption key. So this is why this algorithm is asymmetric in nature. So let's try to perform those calculations also. Now let's assume that based on all these above values, we are considering an encryption and decryption process as follows. So the process is that we are considering every alphabet as number value. So we are saying A equals to 1, B equals to 2, C equals to 3, D equals to 4, E equals to 5, F equals to 6, and so on and so forth, right? So what we are doing is we are just assigning numbers to the alphabets, because since mathematical calculations are required, we need to convert the alphabets into numeric values. Okay. So now let's say we want to send F as the plain text. Okay. So we are considering the PT, that is plain text F, which is corresponding to 6, right? So according to our conversion of alphabet to numbers, F is assigned number 6. So this is the plain text, which is F, which is equal to 6. Now again, for simplicity purpose, we are only using one alphabet, because if we use more than one alphabet, the calculation becomes very tedious. And I just want to show how the encryption and decryption will get you back the same plain text. Okay. So for demonstration purpose, we are using simple values. So now substituting all the values in this equation, the ciphertext CT is going to be equal to PT, which is 6 over here. You can see 6 raised to E. Now from the algorithm, we've found that E is 5. So 6 raised to 5 mod, and n value is 119. Now again, you can use your scientific calci to calculate all these values. I've already calculated mine. So from this, the ciphertext that we are getting is equal to 41. Okay. So this is the result of encryption, that is encrypting F, which was 6. We got the ciphertext of CT equals to 41. Now for decryption, this formula is used, that is PT is equal to CT raised to decryption key mod n. So let's see how that works. So in that case, PT is going to be CT, which is 41, raised to D. Now let's see what is D. D is 77, and again mod 119, right? So again, I have already calculated these values. These are very large values, but if you calculate on the calc, you'll get the value of 6, which is the original plaintext, and you'll get this value back. And the reason why you'll get this value back is because of these formulas, and they are made in such a way that mathematically they give you back the value, and that's how the RSA algorithm works. Okay. And it is just made complex because these numbers are very large actually, that is P and Q values are very huge. So to calculate or for a hacker to crack that number, it is very difficult. So yeah, this was the whole process of encryption and decryption in RSA algorithm, and you can see that two different keys are used for encryption and decryption. That is, for encryption E was used, that is the public key, and for decryption D was used. Now in the scenario of asymmetric key, this encryption public key would be of Alice and this decryption private key would be of Bob. Okay. Similarly, for the reverse case, Alice would have her own private key and Bob would have his own public key also when it comes to reverse communication. That is when Bob wants to send something to Alice. And by that I mean this scenario, that is Alice would have the key of KE equals to 5, that is the public key, and Bob here would have KD, which is equal to 77. So Alice would use this KE public key encryption over here to encrypt the plain text, get the ciphertext, send it to Bob over the internet, and Bob would use this KD over here to decrypt the ciphertext, get back the plain text and read the message. So yeah, that's it for this video guys. I hope you understood the entire RSA algorithm. What is the basic crux, that is the mathematical logic behind the entire working, how asymmetric key cryptography works, and we also saw a basic example of RSA algorithm. So by using some basic and small prime numbers, we are able to prove that encryption and decryption is possible. So thanks for watching guys. If you like this video, please give it a thumbs up, share it with your friends, and if you haven't yet subscribed on this channel, make sure you subscribe so that you get notified whenever I upload a new video, and for that you can also turn on the notifications. So thanks for watching guys. I'll see you guys in the next video. Peace.